as we learn things, we make mistakes and we have to unlearn them. Well, we're going to do a little bit of that today. And we're going to focus on a trigonometric way to describe all this stuff. It actually will make it easier. I know you think that's going to be horrible. Actually, it's going to help us out. Let's kind of look at this diagram backwards. No arrowhead. That means all the time that I drew a ray, and that's probably a good idea not to draw them, but just use algebra, all of those rays should not have an arrowhead, meaning that if this is -1, then it's still the same. So that means the arrowhead could switch back and forth and it's still the same ray. So let's start off with that. Now remember, relative magnitudes and relative phase, that's what determines a ray. So we have to have both of those things. And here's a way we can represent alpha as a quantity, a magnitude times e to the I phi, and beta as r2 e to the I phi 2. And you can imagine those things being plugged back in over here. So let's move to the next page, and it's really going to blow your mind. So I'm going to take it as slowly as possible. It took me a couple days just to sort it all out. Okay, comfort zone. Alpha times the 0 basis vector and beta times the 1 basis vector. Now remember, these were complex quantities. So I'm going to choose it this way. Cosine theta, let's try to see if this works. Cosine and sine for the magnitudes, and this guarantees that cosine squared and sine squared equals 1. Oh, a trig identity. Oh my gosh, trigonometry. Why do we want this? Now I've only got one phase on here. How can I get by with one phase? Well, all we want to do is recognize the relative phase. And so all of this should equal a ray. This is a ray, no arrowhead. So remember, if we multiply this times -1, it's the same thing. That's really important for what I'm going to do next. Now, every unique ray should be determined by an angle between 0 and 2 pi and an angle between 0 and 2 pi. In other words, theta between 0 and 2 pi and phi between 0 and 2 pi. Each one of those should be a unique ray. Remember this, ray. Okay, let's go down here. Let's try to see if this works. 0 between 0 and pi, between 0 and pi, we get unique rays. Okay, does that make sense? Unique rays between 0 and pi, because the sign would be different on those things. So let's say that we get to pi and cosine is -1. What does that do? Well, that switches the direction of the, no it doesn't. It doesn't switch the direction. It just multiplies it times -1. See how confusing that is? So these give us unique rays. But as we go from pi to 2 pi, and notice each one of these, I say that the phase could be 0 to 2 pi, all of these are repeated. So even though we've got unique thetas over here, we don't have unique rays represented. And Do we want to repeat rays? No, no, no. We want those to be unique. So here's what we do. We divide theta by 2. Now let's see what happens here. Between 0 and pi, which is really going to be 0 and pi over 2, unique rays. No problem there. No problem there. Between pi and 2 pi, do we have unique rays there? Between 0 and 2 pi? Yeah, that's correct, because it's actually pi over 2 to pi. See, that's where the unique rays were up here. Now, what about, oh wait, we've done it. We've done it. 0 to 2 pi, we have unique rays. Now what about all this stuff? Well, that's coming back over again, but that's understood that we're going to start repeating. You go around the unit circle, you hit 2 pi, and then you start repeating again. So these are repeated, but who the heck cares? Is that clear enough? Freeze the screen and prove this to yourself.